Okay, let's begin. I'd like to begin with some preliminary remarks. I'd like to explain our main provisions to language modeling in order to make it clear from the very beginning that they are different from the machine learning mainstream approaches, and also to the many approaches to common sense modeling. First, our long-term aim is the development of an integrated functional model of natural language. This model includes both major linguistic capacities of humans, that is language understanding and language generation. Second, this model is mostly based on explicit knowledge. Such knowledge permits to build a transparent mechanism whose functioning can be represented in an intuitively understandable way. And this is what differs our approach to the black box approaches where that are not intuitive. This knowledge is acquired manually because automatic extraction of this type of knowledge is unfeasible at the moment. And the third point is that the aim of building an integrated model that covers all language levels from morphology to semantics requires that all its components be perfectly coordinated with each other. And as a consequence, all publications on the model, even the ones treating very special issues, should be conceived as building blocks of the same edifice coordinated with what has been done before. Our major aim is the modeling of text understanding. And here, a very important role play inferences, because we proceed from the idea that the depth of understanding is determined by the inferences that we can draw from the text, that is, by their number, variety, and depth. The model should be able to explicitly represent all reasonable inference that it makes. We make two types of inferences: the strict inferences that are valid 100%, and plausible expectations. For example, when I say I broke the cup, we can conclude that the cup is broken, that is, it lost its integrity, and that follows from the meaning of the words. It cannot be otherwise. But if I say I dropped the cup, I can also make this inference that the cup is broken, but this inference has a different status. That is not 100%, that is only a plausible expectation. The inferences are made due to different sources. There are two types of sources: the linguistic knowledge, that has meaning of linguistic units, mostly words, and non-linguistic knowledge, that is knowledge of common sense axioms, background knowledge, knowledge of subject domain, etc. In order to make all these inferences, one needs to first explicitly represent both types of knowledge and then implement a reasoning mechanism. There are several data sets for common sense reasoning. We will be working with one of them, the most recent one, which is called Triangle-COPA. This data set was specifically designed as a development test set and not as a test set for competitive evaluations. It was intended to aid in the logical formalization of common sense knowledge that is needed to correctly answer questions. It differs from other data sets developed for common sense reasoning in two important ways. First, it does not contain only natural language questions and answers, but also there these texts are translated into the first order logical formulas. This eliminates the need for sophisticated natural language processing. And the second difference is that the domain of situations referred to in the questions is very much constrained. The world they describe this world is very narrow, very poor. And this allows researchers to concentrate on common sense reasoning. What does it look like? This is a set of 100 problems for logical formalization of common sense psychology. They describe a brief sequence of actions between three geometrical shapes. The heroes of all these texts are two triangles and a circle. They perform various actions in and around a room with a door. Each text, each of these 100 texts consists of one statement and two alternatives connected with the statement. One of these alternatives is much more plausible than the other and provides a better explanation of the statement. Our task is to computationally determine the correct alternative. An example. The statement, a little triangle and a big triangle are next to each other. A circle runs by and pushes the little triangle. The big triangle chases the circle. And the question, why does the big triangle chase the circle? And there are two alternatives. Alternative one, the big triangle is angry that the circle pushed the little triangle, so it tries to catch the circle. And the second alternative, the big triangle and circle are friends, and the big triangle wants to say hello to the circle. As we see, all the three texts, the statement and both alternatives, are supplied with logical forms. We can also see that sometimes logical forms are a very simplified representation of the text. For example, the first alternative, we see that the English text is much more, contains much more information than its logical form. Well, we are aware of two related papers. I will comment now on one of them that I consider more important, very significant. That's the paper by Gordon of 2016. It uses logical and probabilistic reasoning. All the knowledge needed to answer the questions is encoded as the feasible axioms in first order logic. I'll give one example. There are several axioms that provide possible reasons why one character could chase another. One of these axioms says that if one person is angry at another person, then the first person will chase the second person with a probability of 0.2. Gordon handcrafted a set of axioms oriented towards specific inferences needed to resolve the test. These axioms ensure correct choice of 91% of alternatives, and this is very good, but this success owes much to authoring axioms specifically for these questions. The axioms are very fragmentary and do not seek to make integral part of some balanced knowledge repository. But that's not the defect of the paper, because the aim of the paper was not to enlarge the knowledge repository, but to compile, to make a new version of the abduction reasoner and show that this reasoner work can solve the problem, provided it is given high quality axioms. And that is why the axioms are of secondary importance for this paper. Our approach is different. We propose to solve the specific Triangle-COPA task by means of a more general instrument, which is devised for quite different purposes. It is easy for humans to answer these questions, not because we learned some specific method, but simply because we understand the text and can apply elementary common sense logic. And this is what we are trying to teach the computer. We are working on the SemETAP, which is a semantic module of the multifunctional linguistic processor called ETAP4. And this semantic model reuses the non-semantic components of ETAP4, that is, morphosyntactic analyzer and the combinatorial dictionary. The resources that the semantic analyzer has are linguistic knowledge, which has a combinatorial dictionary complemented with semantic information and rules of different kinds, and extralinguistic knowledge, which is ontology, repository of individuals, and inference rules. Here, inference rules plays the major role because, as I mentioned, the more inferences are made, the deeper the understanding obtained. The semantic analysis constructs two kinds of semantic structures, two types of semantic structures. First, there is basic semantic structure that interprets the text in terms of ontological concepts, and the enhanced semantic structure that complements the basic semantic structure with a series of inferences. The inferences are very important because they can restore omitted semantic elements and answer questions even if the answer is not contained in the text directly. For this paper, enhanced semantic structure is the most important representation because it is the enhanced semantic structure that contains all the inferences that the knowledge available permits to make from the text and from the context. This approach determines some important features of the way we handle Triangle-COPA texts. First, the aim. Our priority is not so much to correctly answer concrete Triangle-COPA questions, but rather we wish to formulate new common sense knowledge, incorporate this knowledge into an integrated natural language understanding system, and test its validity. And second, we want to show that the Triangle-COPA text type can be resolved by a general purpose semantic analyzer. Then the method in processing Triangle-COPA texts, we implement the full scenario of natural language understanding, starting from the raw text and not from manually composed, simplified logical forms. To do that, we have to translate the original English texts into Russian because the semantic analyzer that we are using is being developed for Russian. This is a more natural task than processing logical forms because it is closer to the phenomena we are modeling, that is, human understanding of texts. Besides, in this case, the task becomes more complicated, not only because we need additional stages of processing, because we are processing the text and not the logical form, but also because logical forms that are proposed often simplify the initial English text, as we saw in the example that I showed before. I have to make some comments on the knowledge acquisition bottleneck, because as is well known, for modeling common sense reasoning, the acquisition of the knowledge is of primary importance. Many projects that are working on common sense reasoning make use of existing resources such as WordNet, FrameNet, Freebase, ConceptNet, and others. But these resources contain very little of the knowledge we need, and that is why we have to develop the knowledge we need ourselves. This task of enormous complexity is very difficult to acquire common sense knowledge, and automatic means of acquiring this knowledge so far are not sufficient to acquire the knowledge that we need. Therefore, the only feasible way is the gradual knowledge accumulation by means of small incremental steps. In this work, we are making one more step in the direction of the development of common sense knowledge repository. The important thing is that the knowledge we introduce should not be ad hoc. It should not be oriented strictly towards the Triangle-COPA texts, but they should retain, this knowledge should retain its validity in a wider context and can be usable for different purposes. Only in this case will the knowledge base incrementally grow and maintain stability. Therefore, when we formulate knowledge, we attach particular importance to do it in the most general way possible. Sometimes we even allow an impairment of the specific case we are dealing with in order to maintain the generality of knowledge. One illustration. Above, I showed one example of the text and one axiom produced in the paper of Gordon. This axiom says, this axiom connects the concepts angry at somebody and chasing, and says if someone is angry at someone else, he will probably chase him. This axiom was most likely introduced for the scene 83 that we saw before. We see here that the statement contains the concept of chasing. The first alternative contains the concept angry, and the second does not. The axiom establishes the connection between chasing and being angry, and that serves as the reason for selecting the first alternative and not the second. So to account for this text, this axiom is sufficient. But if we want to build the knowledge base for a wider class of situations, not only for this text, then it is desirable to give more information on the concepts and link them in a more general way. Let me show how we do it in SemETAP. I will show you the definitions of chasing and anger. These definitions are formulated in the system in a special language for inferences that is called etalog. For clarity, I will translate these definitions from etalog into English. The first definition is the definition of chasing. Agent 1 moves towards agent 2 in order to come in contact with him and perform action 1 upon him, which is bad for agent 2. Agent 2 moves from agent 1 in order to avoid coming in contact with him. The definition of anger is as follows. Agent 1 is an intense negative emotional state with respect to object 1. This state may be accompanied with agent 1 frowning and raising his voice. Besides, if object 1 is a person, if we are angry at somebody, then agent 1 may perform action 1 upon him, which is bad for object 1, for this person. But also, object 1 may be a situation. We may be angry because some situation takes place. And in this case, agent 1 probably feels anger with respect to the initiator of this situation. Besides that, we must say that if object 1 is a situation, then this situation takes place irrespective of whether anger of agent 1 takes place or not. This last proposition describes the facticity of anger. What does it mean? It means that if we have two sentences, Mary is angry that Peter didn't accept her proposal, and Mary is not angry that Peter didn't accept her proposal. In both cases, we can conclude that Peter did not accept her proposal. We can make this inference, and that is an important inference to make. Well, what do these definitions give us? First of all, they permit to make many inferences. For example, if we take the sentence, the dog is chasing the rabbit, these definitions allow us to make many conclusions, many inferences. Is the dog moving? Yes. In what direction is the dog moving? Towards the rabbit. What is the dog's objective? To come in contact with the rabbit and do something with him. What can be expected if the dog comes in contact with the rabbit? It will do something that the rabbit will not like. What is the rabbit's objective? To avoid the contact with the dog. All these and some other inferences can be made based on these definitions 1 and 2 above. If this sentence has a continuation, for example, the dog chased the rabbit, but it did not succeed. In this case, we can conclude that the dog didn't come in contact with the rabbit. Turning to anger, if we see that Peter frowns at Mary, we can conclude, based on the definition 2, that he is probably angry with her. So these definitions allow us to make many different inferences, and it's obvious that the axiom above from the paper of Gordon permits none of these inferences. If we come back to scene 83, it's easy to see that these definitions reveal semantic agreement with the statement and the first alternative. The first definition entails that since the big triangle chases the circle, he probably wants to do something bad to him. And the second definition entails that since the big triangle is angry that the circle pushed the small triangle, he is probably angry at the circle himself and will do something bad to him. So we see that there is semantic agreement between the statement and the first alternative. In both cases, we can conclude that the big triangle will probably do something bad to the circle. And we cannot discover any semantic agreement between the second alternative and the statement, and therefore the first alternative will be preferred. We performed an experiment with this knowledge. First of all, in order to determine the value of this test as a development set for acquiring common sense knowledge, we split the preparation of the experiment into 2 steps. In the first step, we described the concepts represented in the Triangle-COPA texts without consulting the actual texts. Accordingly, we didn't know what common sense knowledge would be needed for these texts. And the second step, we used Triangle-COPA texts as a development set. We consulted them for knowledge acquisition, and the knowledge acquired at the first step was complemented with new axioms, which we didn't notice before. For example, this was the case with the axiom, if somebody touches somebody, he probably wants to attract the other's attention. This is a reasonable axiom that didn't occur to us before, but that is general enough. It is not oriented specifically to the texts of Triangle-COPA. So when formulating the axioms, we took care not to construct ad hoc axioms. After that, we carried out experiments on the selection of an alternative using knowledge acquired at steps 1 and 2 separately. We constructed all the enhanced semantic structures of all the alternatives and all the statements. And then we applied a selection algorithm that compared enhanced semantic structures of the statement and of each alternative and calculated their semantic similarity. And then selected the alternative that manifests more similarity with the statement. The first step didn't give very good results. We got only 53.5% of correct alternatives. At the second step, the results are much better. It is 80.5% of correct alternatives, of which 76 are correct, 15 wrong, and 9 random choices were made. The sources of error are two. First, incompleteness of knowledge. Still, we didn't provide all the knowledge that could be provided. And second, some axioms that would ensure correct choice of the alternative were not considered general enough and were rejected and not included into the general knowledge base because they are too specific and too oriented towards the concrete texts. And now conclusions. First, our method implements the full scenario of text understanding, which includes morphosyntactic and semantic analysis and drawing inferences, as opposed to other solutions which are dealing with human authors' simplified logical forms. Our analyzer applies to raw text, and the success rate is reasonably high. The alternative is chosen in 2 stages. First, we build the enhanced semantic structures of all the texts that we want to compare. These structures contain all the inferences that can be produced with the knowledge available. And then we calculated semantic agreement between the enhanced semantic structures and selected the alternative that shows higher agreement with the statement. The semantic agreement is formulated in intuitively clear terms and they are understandable and can be checked by humans. Satisfactory results that we obtained show that a general purpose semantic analyzer can solve specific problems if it is supplied with high quality knowledge. Explicit knowledge about the meaning of concepts and about common sense is of primary importance. During the work, the knowledge base of SemETAP was incrementally increased, so these axioms will be used in subsequent projects. The knowledge acquired is not task specific and can be deployable in multiple scenarios. And the last thing is that an important result that we found is the discovery that the common sense knowledge needed for inferences, even in a very narrow domain, cannot be acquired without thorough examination of texts belonging to the domain. Thank you very much for your attention.